So welcome back. Hope you all had a good weekend. Hope you're transitioning into the in-person classes smoothly now that we've got a week under our belts. One thing I'd like to do right now is actually just go through our Canvas webpage just to point out where certain things are located. I know a lot of you have already gone through all this before and you know where to find everything on Canvas, but in case you haven't, let's just go through it right now. So on the Canvas homepage, the first thing you'll see when you log in is this. At the very top, there's some announcements. So I typically make an announcement every week or so on here. At the very top of the page under where it says Welcome to Physics 44, you can find a copy of the syllabus just by clicking there. And there's a long list of student resources that you can find in this document here. It's kind of too long to even go through here, but if you need help with anything from counseling to financial services to mental health services, it's in that document, okay? So you know where to generally go if you just need help outside of class with anything. I also have just the schedule of when our lecture and lab meetings are. Okay, this is really important. I know a lot of you have seen this already, but if you click right here, this takes you to a page where all of the lecture recordings are compiled. So as I mentioned, every single lecture, I'm going to record it just so in case you have to sit out due to sickness, you can watch it from home and not fall behind on the material. So right now we have both recordings from last week. In about 2 hours or so, you're going to see the recording from today up here as well. So this is just a list that's going to keep growing longer, and I'll just put one link after another on this list. Okay? Has anyone gone and seen any of the recordings yet? Okay. So a couple other things to note. My office hours are here and a link to my Zoom meeting. You can find that. So literally you can just click that link, and if it's during my office hours, that will take you to my office hours. All right, next we have the schedule of events. So every day where we have a class meeting, I tell you what we're doing in lecture in terms of what material is actually being covered and what we're doing in lab. And notice there are clickable links within here as well. So under lecture, what you're going to see is a link to my actual slides that I go through. So if you click, for example, the very first link, these are the slides we went through on the first day of class and the second day of class, which was all about measurement units and problem solving. If you click under the lab, this was our first lab activity. And I'm always going to post this stuff at least a week in advance so you can read ahead about what we're going to do on any given week. And then also keep in mind the assignments are always in this last column here. So if you don't write down on what I put on the board here, what the upcoming homework assignment is, you can always find it on Canvas, as well as any worksheet that goes along with the assignment. You can find that here. I guess one thing I forgot to mention is there's also a link to the textbook right here, so you can read the textbook within your browser if you click that link. So basically every single bit of course material is going to be found on Canvas one way or another. So it's all kind of laid out on the homepage, but also if you go to Files, it's organized in folders. So however you want to look at this stuff, whether just through the clickable links on the homepage or by going to the files, it's up to you. It's all there. Okay? Last thing is discussions. Some people have utilized this already, which is great. Every week, I'm going to open a discussion board. And again, discussions are always optional. These are just here in case you want to ask me a question or ask a question of your classmates. So utilize that whenever you feel like you need a question answered. All right? So now we know where to find everything on Canvas, right? Any questions on this? Okay, so a couple other things. The homework assignment for next week is up on the board. That's going to be due on Tuesday of next week. So there's the worksheet. You can collect that from the front of the room. That's part of the assignment. And I think with that said, we're ready to get back into the lecture. So there were a few slides that we didn't quite get to last week in the chapter 1 lecture that I'd just like to finish off with here today. And then we're going to move on to the next topic, which is kinematics, and that's actually covered in chapter 3. So we're going to finish up chapter 1 here. Should take only a few minutes. Then we're going to move on to chapter 3 of the textbook. Okay? So if you recall, the last thing we were talking about in Thursday's lecture was this idea of dimensional analysis. This idea that you can look at an equation that relates different physical quantities, and you can find out certain things about that equation just by considering its dimensions. In other words, what type of quantity are we dealing with? Okay? So I want you to consider this equation. We have d is equal to 1/2 times at squared. And here, the variable d represents a distance traveled. T represents an amount of time that has elapsed. And a is some kind of constant that we're not quite sure of. The question here is, what are the dimensions of that constant? So actually for this one, we're just going to go through it together on paper right now, and then I'll ask you another one where I'll let you guys try it out, okay? So there's the equation. We know what d is, we know what t is, and we're going to try to figure out what type of quantity is a. What dimensions does it have? Okay? So let's go through it. Start by copying down the equation, which says d is equal to 1/2 times at squared. And there's one thing we know about any type of equation in physics that relates physical quantities. The left-hand side and the right-hand side better match in terms of their dimensions, right? So I can set a distance equal to another distance, but I can't set a distance equal to a mass. That doesn't make any sense, right? So what I'm going to do is put little brackets around the d, which says, this means I just want to find out what dimensions d has, okay? And that better match everything on the right-hand side multiplied together. So that should be the dimensions of 1/2 times the dimensions of a times the dimensions of time, which is also squared. Okay, so I'm just really expanding that all out. But all I'm saying is the dimensions on the right and left have to match. Good so far? Now, dimensions are L, M, and T. We have length, mass, and time as our sort of base dimensions. So distance, that's just a type of length, right? So that has dimensions L. What about this factor of 1/2? What do we do with that? Yeah, the half is just a number. It's what we call a dimensionless quantity. It doesn't have any dimensions. So we can actually just move on to the next term, which is A. We don't know the dimensions of A, so I'm going to leave that as unknown. See what I did there? And then T, well, that's a time, has dimensions of time, but we're squaring it. So what does this tell us? This tells us that whatever this constant A is, it has dimensions of length divided by time squared. Okay? And for anyone who's taken physics before, do you know what this thing A is called?
Acceleration.
It's called an acceleration. And it's a distance over a time squared. We're going to learn about that in chapter 3 as we move on to that. But any questions on how this works with dimensional analysis? Okay, let's do one more. So here, we're talking about something called population density. You may have heard this before. Population density is just the number of people that live in a given city or region divided by the area of the land mass in that region. That's your population density. So how densely clustered are people? My question for you is, what are the dimensions of population density as a quantity? What dimensions would it have? So take, let's say, a minute or two, try to work it out, and see what you come up with as far as what the dimensions of this thing are. And if you're not sure, talk about it with the person next to you. See if you can come to some kind of consensus. So just think of number of people divided by area. What dimensions does that quantity have?
what does M equal to? What's like?
M would be a mass.
Mass?
Yeah,
Like it has to be like a masses in kilograms or grams, or mass of as any other.
when we talk about dimensions, we don't care about the units.
Okay.
Yeah, and M is not necessarily involved in this, but some of the answer choices it could be, right? All right, so here, at this point, let's put it to a vote, okay? And again, if you're not 100% sure, just go with what you're leaning with the most. All right, who would say it's answer choice A? This is like a length squared type quantity. Answer choice B, it's a mass per cubic length quantity. Okay, answer choice C, inverse length cubed. D, inverse length squared. Okay, what about E? Okay, so it's actually D. I think most people said E here, which these are kind of closely related, but not quite the same thing. So here, let me just write it down in words. Population density is, we just count up the number of people, and then we divide out the area of the land that all those people live on, okay? So let's do what we did before. Let's say if we want to know the population density, the dimensions of that thing, better be dimensions of number of people divided by area, okay? Now, when we talk about the number of people, just literally counting up how many people live in a certain city, country, whatever, what kind of dimensions does that have? It's what we call a dimensionless quantity, right? If I just count things up, that's just a pure number. There's no units attached to it, okay? So on top, we have a purely dimensionless quantity. We don't have a mass on top, notice. We just have a dimensionless quantity. So I'm going to just put a 1 to stand in place for a dimensionless quantity, okay? And then area. What are the dimensions of area? Yeah, an area is a length squared. Regardless of what kind of area we're talking about, right? I could be measuring the area in square centimeters or square meters, square miles. Area is just a length squared, regardless of what type of unit we're using. So because we're just counting up numbers of people on top and then we have a length squared on the bottom, we could just as easily see this as L to the minus 2, okay? So the point is there's no mass on the top in this particular case. We good on that? Okay then, so that's going to be all for this very first lecture, but there is something I want to point out about my lecture slides in general before we move on. Okay, so usually I like to cover a bunch of material from a specific chapter of the textbook with kind of some examples sprinkled in. But at the end of every lecture, if you ever have seen the slides I posted, towards the end I have a bunch of practice problems. So what these are here for is, in case we have extra time, we can spend some time in class just going through some additional practice problems. As it stands right now, I think we need to just move on to the next chapter, but just realize that these are here, and you can do these as you study for a test or quiz. And I'm also going to post the answers to all of these problems. You can find those on Canvas, okay? So these are just here to help you study, basically. We'll try to get through them, a handful of them in class if we have time, but just know that these are here at the end of every lecture, okay? So with that said, I'm going to move on to the next chapter we're covering. So the next chapter we're covering in the textbook is chapter 3. So we already covered chapter 1. We're going to jump ahead to chapter 3. We are going to go through chapter 2 at some point, but it just makes sense for me to go in this order. And the topic is kinematics in one dimension. So let's get into it. So the first thing I want to do is just define some words. What does this thing, kinematics in one dimension, actually mean? Let's really break that down so you understand where we're going over the next couple weeks. So when we study motion, which is what we're going to be doing in this class, we're going to be studying motion in general. we can divide that study of motion into two parts. We've got what's called kinematics, which you can think of as just a description of motion. So we're describing like what the velocity of an object is, or maybe where an object is located, what is its acceleration, things like that. Those are just features of the way it's moving. But dynamics takes it a step further. Okay, so kinematics just describes how something is moving. Dynamics gives you the reason why something is moving the way that it is. It's in other words, dealing with the causes of motion. And we're not going to get to dynamics until I think the 7th or 8th week of class. So until then, between now and then, we're going to be, strictly speaking, dealing with kinematics, okay? By the time we get to dynamics, you'll learn about Newton's laws, which is sort of the framework that we work in for dealing with that. Okay, so if we're doing kinematics in one dimension, what do I mean by one dimension? So the number of dimensions in a space, that's just how many numbers that you need to give me in order for me to be able to locate somewhere in that space. Now that may seem kind of abstract, so let me give you two examples, and hopefully it's clear when I give you the two examples. So when I talk about one dimension, okay, let's say we're thinking about this x-axis right here, okay? And you can be located at any point along that x-axis. Well, if I tell you the x-coordinate, like let's say x equals -2, that's all you need to know to locate where I'm talking about in one dimension. Okay, so that's why we say it has dimension 1. You just need one coordinate. If I were working in 2 dimensions, instead of just along the x-axis, let's say xy plane here, then I would need to give you 2 numbers if I were to tell you where in the xy plane I'm talking about, right? I need to give you the x-coordinate and the y-coordinate. And then you can probably see where this is going, right? If I'm in 3 dimensions, I need to give you 3 numbers, x, y, z, to tell you where we're located. So that's the idea. Right now, we're dealing with kinematics in 1 dimension. So straight line motion, in other words, motion along the line, not anything more complicated than that. We're going to get to 2 dimensions and 3 dimensions later on. Okay, so as I said, kinematics in 1 dimension, that means we're describing some kind of motion. That's the kinematics part. And the 1 dimension part means the motion is happening in a straight line. Okay, just straight line back and forth. And let me give you some examples of, situations where we're dealing with kinematics in 1 dimension. So let's say you're driving your car on a straight section of the road and you hit the brakes and you come to a stop. Well, that's motion along a straight line. So kinematics in 1 dimension would be sufficient to be able to describe that, right? Here's another one. Just drop something, have it fall straight down. I'm going to drop a rock off a cliff, right? That object is moving in a straight line. It happens to be a vertical line like this. But the point is, it's straight line motion, okay? Another example would be if you're sliding down a ramp. You're just moving in a straight line. It happens to be angled, but that's another example. Okay. One other thing before we just sort of move on from the setting the stage. From here on out, and basically this is going to apply throughout the entirety of this class. We're only going to start changing this assumption when you get to physics 45. So for the remainder of this class, we're going to treat all moving objects as if they're what I call point particles. Okay? So any moving object you're keeping track of, it could be a person running, a car driving down the road, we're going to treat it as if it's just a point with no size. And that's going to help us simplify some of our equations. Let me explain how that's the case. So first of all, if I want to know where an object is located, let's say a car, what am I talking about? Where's the front of the car located? Where's the back of the car located? It's kind of ambiguous, right? If the car is just a little point in space, it's not ambiguous where it's located, is it? Okay? Another thing is, if you have an object that is not a point, like, I don't know, this pen here, it can do all kinds of things. It can rotate around, it can potentially vibrate. we can ignore those types of motion when we're just treating everything as if it's a little point in space, okay? So again, physics 45, we're gonna start to talk about these things, but for now, we're just gonna treat every object as if it's a little point in space. That make sense? Okay, so what I'd like to tackle now that we've set the stage in this lecture is some basic definitions. So first thing I'd like to define for you is something called position, and then I'd like to define for you something called displacement, and it's pretty important to know the difference between these two things, okay? So let's start with position. What is the definition of position? Well, the position of an object is just the coordinates that I give you that tell you where that object is located. Now, right away, we're talking about coordinates. So how do we actually construct a coordinate system to keep track of where something is? Well, first of all, you need an origin. You need to know where 0 is located within your coordinate system. That's what we mean by the origin. And you need to tell me what is the positive direction, what is the negative direction. Once you've established that, we have a coordinate system. And then I can tell you where something is located in that coordinate system. So here's an example, right? Just the x-axis. Maybe this is my coordinate system. I'm putting the origin right here. So then I can keep track of how something is moving along that x-axis. I can tell you where it's located at different moments in time, right? That would be its position. And remember, in one dimension, all you need is one number. You just need x, and then you know where on this line you're located. If I were in, let's say, 3 dimensions, like I was saying before, you would need 3 numbers. My coordinate system would be an x-axis, a y-axis, and a z-axis, all perpendicular to each other like this. And the origin would be where all these axes meet, like this. But again, once you've sort of set this coordinate system up, you can locate where something is within the 3D space by just giving me an x, y, and a z number. So, make sense? Okay, so for now, we're going to limit ourselves to 1 dimension. Later on, we're going to do 2, 3 dimensions, but for now, we're just in 1 dimension. So let's define something called displacement in that case. Displacement is what we call a change in position. So you move from one position to another. The amount of change in your position is what we call the displacement. It's given by delta x. So this is really important. This is going to come up all the time in physics. Are we all familiar with this sort of delta notation? If I put a delta in front of the x, what I'm saying is we're taking the final x value minus initial. Delta just means do final minus initial. So if I take my final position where I end up, subtract off my initial position where I start, that's my displacement. Now, if you think about it, displacement could easily come out positive or negative depending on which way you're moving, okay? So in other words, the sign of delta x tells you which direction you've moved in. So let's take a look at 2 examples. First example, I have an object. If you see this red dot, that's the initial position where it starts. And this blue dot is the final position where it ends up. So in example 1, what would our initial position be? Just read it straight off the line. What would it be?
-2.
So it's, we're starting at -2 meters. That's xi. And then where do we end up? What's our final position in this picture?
1.
Okay, 1 meter. So what's our delta x?
3 meters.
Yeah, it's just x final minus x initial. So I'm going to take 1 meter minus -2 meters, which, like you said, is 3 meters. Again, came out positive. That tells us we've moved in the positive x direction. That's what the sign is indicating to us. All right, in the second example, what's our initial position? Where do we start? Right here? Positive 3 meters, and where do we end up? End up at -1 meter. So if we do final minus initial x value, for that second case, we have -1 and then -3, which is minus 4. So that just says we moved 4 meters in the negative x direction during this time period. Make sense? That's displacement. Just take your final minus initial position, tells you how far you've moved and which direction you've moved in. Okay. Now, it's really important to just actually state that displacement is not exactly the same thing as distance that you've traveled, okay? Because if you think about the way we've just defined displacement as x final minus x initial, all that matters as far as your displacement is concerned is where you start and where you end up. The path you took has no bearing on your displacement, right? It just matters where you start and where you end up. However, distance, if you think about it, does depend on the path you take, doesn't it? Like if I drive from my house to the store and then back, well, I start and end at the same position, don't I? So what would my displacement be? Be 0, right? If you start and end up at the same position, technically your displacement is 0, but we certainly wouldn't say you've traveled 0 distance, right? So distance is something kind of different. Distance, it actually matters the path you take. It's the total length of the path that you take to get from your starting point to your ending point. So here's a great example of this. Let's say I start at position A right here, end up at position B right here, and then let's say this dashed blue line is telling us the path we took to get from A to B. Okay? You can literally just imagine laying down a measuring tape exactly along that path and seeing how much distance you've covered. That's distance, of course. Displacement just, again, depends on where I start and where I end up. So it would just be giving me this chunk of that, as opposed to the length of the entire path. Does that make sense? So there's a difference between distance and displacement. It's important to keep in mind. Okay. So, question. You're on a track. You run around that track 4 times for 4 complete laps. What is your displacement for that run? And the track is a quarter mile long, let's say. It's 0, right? Yeah, you're all saying it. And why is it 0?
You started and ended at the same place.
Yeah, because you started and ended at the same place. So by definition, your x initial and your x final are the same thing if you start and end at the same place. So your displacement is 0. Okay? All right, so that hopefully is pretty straightforward. Again, we've covered position, where are you located, covered displacement, that's your change in position that's happening as you move around, and then that's different from distance, important to keep in mind, okay? So now we're going to get to some other definitions, particularly velocity. What does velocity tell you? It tells you how fast are you moving, and also it has information about which direction you're headed towards, which direction are you moving in. So that's what we'll tackle next. Just define this. Can anyone guess what comes after velocity? What do we define after this?
Acceleration.
Yeah, then we'll define something called acceleration. Now, we're really going to get into the details of this, so it might not be until like the middle of Thursday that we've defined everything, and then we're getting into some equations. Okay, so we're gonna take it kind of slow with these definitions. Okay, so like we said, velocity, it's telling you, it's a number that tells you how quickly you're moving, and also it has information about what direction you're moving in. Okay, so let's take that definition and turn it into a more concrete equation. Okay, so here's the setup. So let's suppose that at time t initial, that's basically, think of that as when we start the clock, that our position is x initial. And then at t final, which is when we stop the clock, our position is x final. Okay? So we have some interval of time, starts at time t initial, it ends at time t final. And over the course of that time interval, there's something called the average velocity that we can define. It's pretty simple, just goes like this. the average velocity in this interval of time is equal to delta x divided by delta t. So, what's delta x? We saw that already. That's x final minus x initial. That's our displacement, right? We're really just taking our displacement and then dividing it by how long it took to do that, delta t, and that gives us our average velocity. So to kind of expand this out, it's x final minus x initial divided by t final minus t initial. So we all clear on the definition? Just delta x over delta t. All right, so what kind of quantity do we have on the top? We have a length. Displacement has dimensions of length, of course. And on the bottom, we have a time interval, dimensions of time. So dimensions of velocity are length over time. And you can express this in all kinds of different units. But in the SI system, we use meters per second. So that's going to be our most commonly used unit of velocity, is meters over seconds. And I just want to remind you, just like delta x can carry a positive sign, can also carry a negative sign, the same is true of our velocity. That can carry a positive sign or a negative sign. And that's just telling you which way are we moving. Are we moving in the positive x direction, or are we moving in the negative x direction? Okay, any questions so far? Okay, so we'll keep it moving. And again, just to remind you, all of these slides are available on Canvas, so you don't necessarily have to copy every last detail off the slides. Mostly just stick to the examples and fleshing things out. Let's take a closer look at average velocity. In particular, I want us to look at how can we look at a graph of an object's motion and say something or determine something about its velocity, okay? So what you see here is something called a position versus time graph. So what that means is on the vertical axis, we have position, which is x. So I know you're used to seeing x on the horizontal axis. X is on the vertical axis in this particular case. And time is what's on the horizontal axis. So you have position x going this way, you have time t going this way. And what we can do is, we can take an object that's moving around and just say, well, at time 0, it's located here. At time 10 seconds, it's located there. And just plot out where it is at every moment in time. And you'll get a little curve that describes how it's moving. So that red line is describing how the position is changing. Now, remember what we just said about average velocity? It's delta x over delta t. That should kind of resemble a slope, if you think about it. Because delta x is going to be the rise of this line. And delta t is going to be the run. Rise over run is a slope. So, in other words, if we take 2 points on this graph, just connect them with a straight line. Let's say I have point A here and point B here. Connect them with a straight line. My delta x is the rise that you see here. It's the displacement that we've undergone. And delta t is the run over here. So the point is, average velocity is just what you get when you take 2 points on a position versus time graph, connect them with a straight line, and you find the slope. Okay? Now think about it. If the line is sloped up, that means we have a positive velocity, doesn't it? It means we're moving in the positive x direction. If the line is sloped down, we have a negative velocity, and we're moving in the negative x direction. Okay? So that's how we can say something about velocity using a graph kind of like this. Any questions on that? Okay, so velocity is a slope. Okay, so we've defined average velocity, haven't we? We've defined it as, if we want to put it in words, displacement over time. Okay? Now you're also going to encounter a term called average speed, which is closely related but not exactly the same thing, which is distance over time. Okay, so average velocity is displacement over time. Average speed is distance over time. So notice the difference, right? When it comes to velocity, that can come out positive or negative, as we've just seen, because you can be moving in the positive x direction, you can be moving in the negative x direction. Average speed, on the other hand, that's always going to be positive, because when we measure a distance, that always has a positive value to it. Okay? We just care about how far you've traveled. That always takes on a positive value, which means this is always going to come out positive. So with that said, let's just do a quick example sort of calculation where we use this definition of average speed. So the speed of light, which is actually the fastest speed in the universe, is 3 times 10 to the 8 meters per second. The distance between the Earth and the Moon is 239,000 miles. So the question I'm asking here is, how long does it take for a beam of light to get from the Earth to the Moon? So if I were to like shine a laser pointer at the Moon, how long would it take before you see a spot on the Moon, in other words? And to do this, we're just going to use the definition of speed that you see up here. Okay? So let's go through it. Okay, so there's an equation that we wrote down in words, which I'll just copy. Speed is distance divided by time. Let's just say that's S equals D over T for short, okay? Now, what variable am I interested in solving for here? T. So I want T equals something. If I solve for T in this equation, what do I get, just symbolically? Let's think about it.
T equals D over S.
Yeah, it's just going to be T equals D over S. How can we see that? Let's multiply both sides by T. We cancel it on the right side. And then let's divide both sides by S. Cancels it out on this side. And so we have T equals D over S, okay? Now, what is the distance that we were dealing with? It was 239,000 miles. But I'm going to do a quick unit conversion for you guys, which is in every 1 mile, there are 1,609 meters. So I'm converting the distance to meters so we can get the units to cancel later on. What does this work out to, by the way? What is the distance to the Moon measured in meters when we do this conversion? So yeah, let's get those calculators out. So here, I'll tell you how this one works out, and then the next one I want you guys to do. So this is 3.846. We'll keep actually 3 sig figs on that. Times 10 to the 8 meters. That's what you'll get if you do this unit conversion. Remember, we want the time, which is D over S. The distance, D, is 3.846, 10 to the 8 meters. The speed is the speed of light, which we're given 3.00, 10 to the 8 meters per second are the units on the bottom. So you can see why I wanted to convert to meters earlier, just so I can cancel here and here. So I get a certain number of seconds. What do I get? I can actually cancel 10 to the 8 also, can't I? So just do 3.846 divided by 3. What is that?
1.282.
Yeah, so 1.28 seconds. That's the light travel time from Earth to the Moon. So not much time at all. Pretty straightforward. Any questions? Okay. So we'll keep going. Keep it moving. I have some questions that I'd like you guys to try out. which involve these definitions. So just before we launch into the questions, remember two things. Average velocity, that's your displacement divided by your time. Average speed, that's the distance you've traveled divided by time, okay? So here's what you see in the figure. We have objects traveling along 4 different paths, starting from some initial point to some final point. And all of these different paths involve the same amount of time, okay? So for object number 1, kind of moves to the right 2 units and then back to here. It takes the same amount of time as, let's say, this object to go from here to here. So in all the different cases, same time is involved, okay? But clearly they're moving along different paths, right? So what I want you to do is rank all of these objects in terms of their average velocities. So let's say object number 1, its average velocity for this motion, we'll call it V1. Object number 2, we'll call it V2, and so on. Just try to rank them. Which one is the biggest? Which one is the smallest? And then which one of these answers gives you the correct ranking from biggest to smallest? Okay? So again, try to work it out. Talk to the people next to you if you need, and then we'll go through it together. So for this, I'm just going to write an equation down that you'll need. V is delta x over delta t. Same delta t for all these cases. They might differ in terms of their delta x. Okay? So start by just thinking about what is the displacement, what is your delta x for each one of these different pictures. Okay, let's maybe talk this one over a little bit, okay? So we're all on the same page. Let's look at object number 1. We don't have to put units to this. Let's just say each line is 1 unit, okay? How far has object number 1 traveled overall? What is its displacement if we just think about where it started and where it ended up? Yeah, object number 1, it just moved 1 unit to the right overall. That would be its displacement. Again, we don't care about the path it took. We just care that if we compare its final and initial positions, that it's moved 1 unit over to the right. We agree? What about object number 2? Same thing, right? It starts here, ends up here, so its displacement is 1 unit over to the right. Object number 3, that one's pretty obvious, just 1 unit to the right. Okay, what about object number 4? 1 unit to the right. So they all move by 1 line to the right. They all have the same exact delta x, right? And we've already said they all have the same exact delta t. So guess what? Delta x over delta t, in all of these cases, will be the same answer, okay? Regardless of what numbers go into that calculation. So which answer choice is the correct one here? C. They all have the same average velocity because they all have the same displacement in the same amount of time, even though they take different paths. Does that make sense? So let me ask you a slightly different question. Okay? Same exact setup. It's the same 4 objects, and they move in those same paths that we saw before. But now my question for you is, how can we compare their average speeds? Let's try to rank their average speeds from highest to lowest and see what the order is, okay? Now remember, Speed is distance traveled divided by time, as opposed to displacement divided by time, okay? So with that in mind, try to figure out what the ranking is. And for this one, really try to get it at your desk to see what the right answer is. Start by writing down what is the distance traveled by each object, okay? Your answer? Yeah. Okay, so in this case, they're not all equal, right? Right. Let's think about 30 seconds or maybe another minute to think about this one. Okay. You all have an answer in mind? Let's put it to a vote. Who thinks that answer choice A is the correct ranking, where it's just basically 1 is the biggest speed and then 4 is the smallest in order like that? Okay. Who says it's B, C, D? Good. I think we got this, right? So real quick, let's just figure out what is the distance traveled by each object. Let's just rattle it off real quick. Object number 1, how many lines does it travel over in its total journey? Yeah, so as far as distance traveled is concerned, for object number 1, it's 3 units of distance, right? What about object number 2?
3.
Also 3 units of distance. So 1 and 2, because they travel the same distance in the same amount of time, have the same average speed for this motion. Okay, what about object number 3? How many units does it travel distance-wise?
1.
1 unit. What about 4? Yeah, so it's 5-ish. You know, it's not exact, but the point is 4 is clearly the greatest distance, right? So, because we all involve the same amount of time for these different paths, the one that has the biggest distance is the one with the biggest speed. So, object number 4 has the biggest speed, followed by 1 and 2, which are equal, and then followed by 3, which has the smallest speed because it travels the smallest distance. Okay? So that's how we want to just think about these conceptually. Okay? So hopefully you're seeing the difference between distance, displacement, and speed and velocity. They're not exactly the same thing. Okay, so next I want us to actually do some calculations of a velocity using data plotted on a graph, okay? So what you see in this graph is the position versus time graph for an object moving along the x-axis. So again, position versus time means x is your position. That goes on the vertical axis like this. Time goes on the horizontal axis like this. And what you're seeing in the red line is just at various moments in time, where is this object located, okay? So we're going to do some calculations. The first calculation I want you to try is this. Calculate the average velocity for the whole entire trip, which goes in time from 0 seconds to 12 seconds over here. What is the average velocity for that entire motion? So take about a minute, try to work it out on paper, and then we'll put it to a vote, okay? Just remember the equation for average velocity. It's delta x divided by delta t. Okay, so this one shouldn't involve punching a whole lot of stuff into the calculator, right? What is the answer? It's 0. The answer is 0. And why is that? Let's talk about why that is. So v is delta x over delta t. That's our average velocity, okay? And delta x is x final minus x initial. Delta t is t final minus t initial. Now, all of these numbers are things we can read directly off the graph. On the graph, where was the object located at the end of the motion at 12 seconds? What was the x value?
0.
It was 0, right? That was our x final. And what was our initial x value? 0. So it doesn't really matter what's on the bottom here. We're going to get 0, right? So here's one way you want to think about this. What does it mean that the average is 0? Well, sometimes it's moving in the positive x direction. That's when you see the line sloping up like this. But other times our object is moving in the negative x direction. So in other words, sometimes it has a positive velocity, other times it has a negative velocity. But the average of all those velocities is just 0. There's equal amounts of positive and negative, averaging out to 0. That's one way you can think about it, okay? What is the average velocity for the first 4 seconds of the motion that you see on this graph? Try to work that out. And you can do the calculation the same way. It's just delta x over delta t. See what you get. All right. So who's got the answer? What's this going to be? So answer choice B, half a meter per second. So let's just do it real quick. Make sure we're on the same page. V is delta x over delta t. So if you look at the graph, x final, what is that? That was 2 meters, right? After the first 4 seconds of motion, we end up at x equals 2 meters. And we start at 0, just like we said before. And 4 seconds is our final time, 0 is our initial time. That's how you want to think about the denominator there. So it's just 2 over 4, which is a half, or 0.5 meters per second. Okay? All right, let's do maybe one more of these. What is the average velocity between 8 and 12 seconds according to this graph? So take a minute, work it out, and see what you get. Okay. So what's the answer?
B.
And it's negative, right? Does that make sense? The line is sloping down. It's probably what we'd expect. In other words, for the last 4 seconds of motion, our x value is decreasing. Must mean we're moving in the negative x direction. Okay. Well, let's just do the calculation real quick. So for this third question, our velocity is, okay, we're doing x final minus x initial. We end up at 0 after 12 seconds. At 8 seconds, we're at 10 meters. That's just something you can read right off the graph. We're at x equals 10 meters. And then what's our delta t? It's 12 seconds minus 8 seconds. So we have minus 10 meters on top, 4 seconds on the bottom, that's minus 2.5 meters per second. Okay. So hopefully you see how to calculate average velocity using a graph of motion like this. Okay, so what we just talked about was something called average velocity. We're going to move on to something kind of related to that, or very closely related to that, called instantaneous velocity. But before we get there, there's a little bit of math background that I want to just refresh you on, okay? We're all familiar with what a function is, right? If you've taken, calc or pre-calc, you talk a lot about functions. Here's how I want you to think about a function for the time being. Just think of a function as a relationship between inputs and outputs. So in other words, you put something into the function, you put in a certain number, or maybe even a whole bunch of numbers, and you get out some number, or maybe a whole bunch of numbers. So you put something in, you get something out. That's a function, right? So, for example, what if I had position as a function of time? That would be x is the thing I'm getting out, and then t, time, is the thing I'm putting in. So if I plugged in t equals 0, what I would get out is the position of my object at t equals 0. If I plugged in t equals 10 seconds, what I'd be getting out is the position of my object at t equals 10 seconds. Now, depending on how the object in question is moving, this function could be all kinds of different things, right? So let's take this as our example. X of t is equal to t squared plus 3, where t is in seconds and x is in meters, okay? So what we're going to do is just a little bit of practice plugging some numbers into this function and getting some things out of it, okay? So for example, let's say we plug in t equals 0. The way I would write that is x of 0, like this, is equal to, I'm plugging in 0 for t, so I'm going to have 0 squared plus 3. So I'll have 3 meters. That's where we start off. And notice, I'm putting that on a graph, so that when t is equal to 0 right here, x is equal to 3. That's a point on the graph that I've just put there, okay? Next thing we're going to do is plug in 2 seconds, just as an example. We'll plug in 2 seconds. So this would be x of 2. That's 2 squared plus 3. 2 squared is 4, plus 3 is 7 meters. And that's another point on the graph. So you see, when the time is 2 seconds right here, the position x is 7 right here. Okay? And then next, we're going to plug in 4, just as another example. So x of 4 is equal to 4 squared plus 3. So that's just going to be 16 plus 3, 19 meters. And that's another point on our graph over here. Okay? And we can kind of see what the trend is. If we connect those points with a smooth line, we can visualize the function. Okay? So we're all familiar with this kind of thing. Any questions? Okay. Let's do an example where we take x as a function of time for some object, and we just make a couple calculations with it, okay? So here we have a rocket sled moving along a track, so it's just moving along a straight line, such that its position is given by this function you see here, x of t. So in this function, we have a constant a. Take the value of a to be 2.10 meters per second squared. Then we have a constant b. Take the value to be 2.80 meters. So we have a whole bunch of questions related to this function. The first question is, what is the position of the sled at t equals 1 second? Next question, how far does the sled move between t equals 1 second and t equals 2 seconds? And then finally, what is the average velocity between t equals 3 seconds and t equals 5 seconds? Okay, so we're going to just take the function we're given and use it to calculate each one of these things individually, okay? So let's go through it. I'm going to start just by copying down what we know. X of t is equal to at squared plus b, right? Where a is a constant, it's equal to 2.10 meters per second squared. B is another constant equal to 2.80 meters. So remember, the first question is, what is the position at time t equals 1 second? So I want you guys to get your calculators out to do the calculation with me, but basically what we're doing is just saying we want to take x, plug in t equals 1 second, and so that's going to give us A, which is 2.10 meters per second squared, times t squared, that's 1 second, square that, plus B, which is 2.80 meters. So can someone tell me what that comes out to?
4.9.
Yeah, it's just 4.90. The units are meters, by the way. See, we have seconds squared on the bottom right here, and then seconds squared on the top right here. So we just end up with units of meters. So that's where the position is at t equals 1 second. The next question is really about displacement between two moments in time. Between t equals 1 second and t equals 2 seconds. So we can take this to be t initial, this to be t final, if you want to think of it that way, okay? Our delta x is going to be x final minus x initial, right? So that's x when we plug in t final minus x when we plug in t initial. That's how you want to think about it, okay? And, well, when we plug in t final, here's what we have. We have A, which is 2.10. I'm going to leave off the units. Hopefully you've already seen how the units work out here. Okay, so it's 2.10 times our final time, which is 2 squared. That's AT squared right there. Plus B, which is 2.80. So again, that's what we get for x when we plug in 2 seconds. But then I want to subtract what we get for x when I plug in 1 second, which is basically the same thing we have up here, but I'll just write it down again. 2.10 times 1 squared plus 2.80. And again, hopefully you see how this works out in meters, right? Now, can someone tell me what that works out to?
16.1.
I'm getting something slightly different. So this whole thing minus this whole thing.
Oh, fine. Oh, whatever.
I'm getting something like 6.3. Okay. So that would be telling us that between 1 and 2 seconds, we move 6.3 meters in the positive x direction, okay? Okay, next, let's do the last calculation, which is average velocity between t equals 3 seconds and t equals 5 seconds. And again, we're going to take 3 seconds to be t initial, 5 seconds to be t final. That's how you want to think about it. Let's remember how this works. V, our average velocity, is equal to delta x divided by delta t, okay? And our delta x is just, again, it's our x value when we plug in t final, minus our x value when we plug in t initial. So that's what I mean here, okay? And then just subtract by t final minus t initial. So here's what's going into this calculation. We have my x value when I plug in t final is, well, 2.10 times 5 squared plus 2.80. That's what I get when I plug in 5 seconds into my x function. And then subtract 2.10 times 3.00 squared plus 2.80, and that's what I get when I plug 3 seconds into my function. And then on the bottom, I'm going to have nothing but 5 seconds minus 3 seconds. So the top units are meters. We've seen how that works. The bottom units are seconds. Okay, so this is a velocity, it's in meters per second. So that's a lot of numbers to crunch. I'll just tell you the answer. It's going to be 16.8 meters per second. So hopefully you see how we did that. Any questions? Okay, so we have a function x of t. We can look at it on a graph. We can just do algebraic calculations like this, and we can say certain things about its velocity, its position, etc. Okay? Okay, so we've got about 10 minutes left. And in that 10 minutes, I'm going to go over something that you may have seen already if you've taken calculus, and you're far enough along in calculus, or you may be seeing it for the first time here, but we're not really going to be going into too much mathematical detail, okay? I'm just going to tell you about what a derivative is and how it relates to everything we've just been talking about, okay? But we don't actually have to calculate derivatives in this class. I just want you to know what it is. So let's say we have a function f of x, just sort of any generic function whatsoever. And let's just plot that function on a graph. So let's say f of x is what's going on this axis, and then x, the x value is going on this axis. And just to visualize something, let's say this black line tells us what the function is, okay? So the derivative of a function is all about the rate of change of your function. That's really what it's telling you. If you calculate the derivative of a function, it tells you how quickly is that function changing, okay? And there's a graphical way to sort of see what the derivative is. If we think about this in graphical terms, the derivative of a function is the slope of the tangent line, okay, to put it real succinctly. So let's say this is the point where I want to calculate the derivative of my function. I want to know at this point right here, what is the rate of change of my function? What I start by doing is I start by drawing a tangent line to my function right at that point. Okay, and in this case, you see it's this red line. That's our tangent line. You guys remember what a tangent line is, what that means? What does it mean?
Straight line between 2 points.
It only touches at one point.
Yeah, it only touches at that one point and nowhere else. Okay, that's what it means to have a tangent line. So here we say the derivative, df dx, is positive because that tangent line has a positive slope to it, right? That's what that means. And what that tells you is the function is increasing. So if you go from here to here, you see the function is increasing in terms of the value that it puts out, right? But let's say we pick another point, let's say over here. Again, draw the tangent line to that point. And you'll see that we get this green line. And that line is sloped downwards. So the derivative of my function here is negative. Okay, so just to reiterate a few things. On a graph, the derivative of your function is basically the slope of the tangent line at a certain point. And if you're sloping up, you have a positive derivative, which means you're increasing. And if you're sloping down, you have a negative derivative, and that means you're decreasing. And if we look at like the steepness of the slope, like is it a super steep line, like almost like this, that means you're increasing or decreasing really rapidly. And if you're kind of flat, that means you're decreasing or increasing really slowly. Okay, so that's the information we can glean from this sort of picture. So do we have any questions? This is really all we need to know about derivatives for this class. Okay, and that brings us to the final definition of the day, which is something called instantaneous velocity. Okay? So remember, I've been putting the word average in front of everything so far, like average velocity, average speed, and so on. The reason for that is, with these averages, what we're really talking about is, on average, what is the velocity in some interval of time, right? So between 0 and 10 seconds, what was the average velocity? It might have been changing over that interval, but we're just saying on average it had a certain value. What if instead of taking an average, we just want to know what is the velocity at one particular moment in time, rather than averaging over a bunch of times? That's what the instantaneous velocity is. It's what was the velocity at some particular instant in time. So the way we deal with this mathematically, and again, this is just a little bit of calc that you may have seen before. We have the average velocity, which is delta x over delta t, right? That's the definition. And delta t is a time interval. Could be really large or really small, depending on what you're dealing with, right? I could be averaging over 1,000 years or over like 1 second. Delta t can just be whatever you want. Let's imagine shrinking delta t until it gets really, really small. That's what I want you to envision. So let's start with this graph right here. On this axis, you have position, x. On this axis, you have time t. And this red curve tells us how some object is moving. Okay? So let's say I want to know the average velocity between this moment in time right here and this moment in time right there. That's the calculation I want to do. Well, that's delta x over delta t. My delta x is what my displacement is. So that's the change in x that you see here. It's like my rise in rise over run. And delta t is the amount of time that's passed. So that's this distance along the time axis right here. Okay? So the slope of this blue line that you see connecting this point to this point, that's my average velocity, okay? How many times does the blue line hit the red line? It hits it twice, right? So when I'm talking about an average velocity, when I draw this line and find the slope, it hits the curve twice. Just keep that in mind for now. But remember, instantaneous means we want to shrink that time interval until it's basically zero. So we're not talking about some interval of time, we're just talking about one instant in time. Okay? So imagine taking these 2 points, just bringing them closer and closer together until they become the same point. That's what I want you to imagine. These 2 points come closer and closer together until they meet and become the same point. Now instead of this blue line hitting the red line twice, it's only hitting it once, right? And so now this is what we call a tangent line. That's the definition of a tangent line. It hits the curve exactly once, right? And what we know is that this slope is now telling us what the derivative of our function is. Derivative is a slope of a tangent line. So to put that all together, when we take the instantaneous velocity, we're taking what's called a limit in calculus terms, where we're shrinking our time interval delta t to 0. And when we do that, we end up with the derivative of x with respect to time. We call that dx dt. So instantaneous velocity is the derivative of position with respect to time. That's how we describe this in calculus terms. Okay? But we're not going to make any kind of calculations with this definition. I just want to put it out there for those of you who have seen the calculus. Okay? Any questions on this? Okay, so let's get to some more practical issues then. As we said, instantaneous velocity is the slope of the line tangent to your curve on a position versus time graph. And there are 2 things we can say about the slope of that line. One is just the sign of it, right? Positive or negative. We went over this already, but I just want to reiterate. If the slope is positive at a certain point, that means your velocity is positive. What does it mean if your velocity is positive? It means you're moving in the positive x direction. If your slope is negative, you're moving in the negative x direction. What if your slope is 0? You just get a flat line like this.
Steady speed.
Yeah, it actually means your velocity is 0. At least for that moment. You've stopped moving, in other words. Okay? So the sign, whether it comes out positive or negative, tells you about what direction you're moving in. How steep that line is tells you how fast you're moving. It tells you about your speed, in other words. So if I have a completely flat line like this, there's 0 speed. If I have a really steep line, that's a very rapid speed, a very fast speed. Okay? That's how you want to interpret this. So let's take a look at this example. We have this graph. We have points A, B, and C on the graph. So at point A, again, we can draw a little tangent line to the curve at point A. And we see that we're dealing with a positive slope. Okay? So we must be moving in the positive x direction at point A. That's what we say here. At point B, Again, if we draw the tangent line, it's completely flat, zero slope. That means the velocity is zero at that particular point. And then point C, we draw the tangent line, we get a negative slope, and so there's negative velocity at that point. But again, if we just compare these, let's say compare point A, point C. At point C, my line is steeper. So it's a greater speed is happening here compared to here, where it's less steep. Does that make sense? Okay. And we're going to end it with a couple really quick questions, okay? So consider this position versus time graph that you see here. We have points A, B, and C labeled, and some times labeled as well, okay? So at t equals 3 seconds, is this object having a positive, negative, or zero velocity at t equals 3 seconds? Negative, because you take the slope of the tangent line, you'll see that's sloping down at t equals 3 seconds. That's this point right here. Therefore, we have a negative velocity, okay? What about at t equals 1 second? We have a positive velocity at t equals 1 second, because if you draw the tangent line to this curve at t equals 1 second, you'll see that it slopes up. It has a positive slope, okay? So positive velocity. Okay, what about t equals 2 seconds?
Zero.
Yeah, it's zero. If you draw the tangent line right there, it kind of goes flat, meaning your slope is zero and you have zero velocity. So real quick, I'm just going to demonstrate something, okay? Let's say that direction is the positive x direction. So going to my right. To my left is the negative x direction, okay? So what's going on in this graph? I start off moving with positive velocity, so I'm going this way, right? What am I doing? Am I speeding up or slowing down according to this graph at first?
Speeding up.
I would say I'm slowing down, because if you look at the steepness of the tangent line, it's getting less and less. And eventually I hit zero velocity, right? So I'm slowing down actually for the first 2 seconds, but I'm moving that way. So, start off with some pretty large velocity, pretty steep line, but then I slow down to zero, right? Something like that. And then what do I do next at 2 seconds? What happens next? I turn around, I stop momentarily at t equals 2 seconds, and I turn around and I go the other way. When I start going the other way, is my speed increasing or decreasing?
Increasing.
And I start going this way with an increasing speed. That's what the graph is showing you. It's important to be able to connect those things. And in the upcoming labs, particularly next week and the week after, we're going to do a whole lot of things like this, where you connect a graph like this to your actual experience of motion. Okay? And that's going to be it for today's lecture. If you haven't turned in the homework already, please do that. Next homework assignment is on the board.